example of this mechanical energy conservation, a situation where there is no work in and no work done by friction. So the example that we have here is the bungee jump. A bungee jump cord is 30 meters long, and when stretched a distance x, it exerts a restoring force of the magnitude kx, so it follows Hooke's law. Great. Your father-in-law, which none of you hopefully have father-in-laws at your age, but we'll go with it. Your father-in-law, mass 95 kilograms, stands on a platform 45 meters above the ground, and one end of the cord is tied securely to his ankle and the other end to the platform. You have promised him that when he steps off the platform, he will fall a maximum distance of 41 meters before the cord stops him. You had several bungee cords to select from, and you tested them by stretching them out, tying one end to a tree and pulling on the other end with a force of 380 newtons. When you do this, what distance did the bungee cord stretch? Okay, so this whole thing's 45 meters tall, but we only want him to go to 41 meters. We only want that cord to stretch to 41 meters. The reason is we want to give 4 meters of space for him. Yeah, that should be plenty of, so you can, oh yeah, fun. Okay, so that's kind of our goal. Of this 41 meters, the unstretched length of that bungee cord, they said was 30 meters. So that means that the cord itself must have stretched 11 meters in this process. Okay. And it asks us, well, if I apply a force to your bungee cord of 380 newtons, how far is it going to stretch? Well, in order to figure out how far it's going to stretch, I need to know the spring constant. So I need to know the spring constant that's going to produce this effect. All right, so let's think about this. It's starting at one point, ending at a second point. So we are going to set up a work kinetic energy theorem problem. So I list out my work kinetic energy, and now I have to cross out any ones that are going to be zero. So no one is pushing my father-in-law off of this. So there is no work in, so they're not like pulling him down or pushing him or anything. We're going to neglect air resistance, so there's no work done by friction. He's not like sliding down anything. He's like falling through the air. At the bottom, he's come to a stop at his maximum stretch location, so there's no kinetic energy because he's come to a stop. He stopped, he just steps off. He doesn't like jump or anything. At the bottom, let's talk about the potential energy. So that means I need to choose my H0 point. So I'm going to choose my H equals 0 point here. All right, so he has 0 potential energy at the bottom, but he does have gravitational potential energy at the top, some 41 meters up. Okay, and at the bottom, the cord is stretched, yes, so there is elastic potential energy there. And at the start here, the cord is unstretched, so there is no elastic potential energy there. All right, so notice how I went through those and I talked about each one and crossed them off. That's what you need to be doing in your head as you're solving these problems, okay? So we have 0 is equal to negative UG1 plus UEL2. All right, so let's get those on opposite sides and then we'll substitute in. So I have MGH is equal to 1/2 kx squared. So let's clarify a few things in here. Our end goal is we're trying to find k, right? The spring constant. And so h is going to be my 41 meters and x is going to be my 11 meters. So let's solve for k. So I have 2 times the mass, which was 95, times 9.8, times a height of 41 meters, all divided by how far it stretched, squared, and it stretched 11 meters, yeah? Okay. And that will give me my spring constant. Type that in my calculator and I get a spring constant of 630.9 newtons per meter. Now my end goal is to plug that back in over here. So I have 380 divided by that 630.9 will give me the distance it's going to stretch on that tree. And so that distance it stretches on the tree comes out to be 0.602 meters. And so you can't have a lot of leeway on that. I mean, this 0.602, that's this much, you know, just a little bit strong, more stretch, and it can add up substantially in this scenario. So there we go.